So good day to everyone. So in this video we are going to start the new unit which of the syllabus of our syllabus, which is called surface tension. So the surface tension is one of the important property and important and fundamental property of any liquid which we considering. So if you take any liquid of small quantity and suppose if the influence of the gravity is very negligible, then the considered liquid is always assumed to form a spherical water drop. For example, if you consider raw water drain drops and small quantities of mercury placed on a glass plate, or actually always try to keep the spherical shape, so that the liquid actually experiences some kind of force which is actually try to occupy a small surface. We actually try to occupy minimum surface area. So suppose if you consider a two-dimensional object, circle is the simplest geometrical shape because it defines only one quantity to define the circle. So if you convert the circle into three-dimensional object, it is a sphere. So the only the radius is actually defined is enough to define a sphere. So that always the linear liquid try to have a spherical shape because of this is a minimum surface area. So this contracting tendency of the liquid surface is known as the surface tension of the liquid. So this surface tension is, as I told, this is a surface tension is a fundamental property of the any liquid or so you can see a large examples of everyday real world examples for the surface tension. For example, when you consider a glass rod which is actually dipped in a water, and if you taken the rod outside, and you can see the few droplets of water is actually sticking with the end of the rod. So these molecules of water appear to be contained in a bag whose surface is made up of a film of water molecules themselves. So that this example shows that the free surface of the liquid behaves like just a film which actually having under tension. This is one of the example for the surface tension. So another example is when water is actually falling slowly in drops from a tap. So you can see that each drop is actually grams form of a tip in this nozzle. This as a drop of water goes inside, it looks like a hanging elastic bag whose surface area is expanding as it fills up. So you can see this kind of shape is actually due to the surface tension of the corresponding liquid. So another example is the spiders which is actually floating on the water. So these water spiders are able to walk on the surface of the water because of their feet produce which is a dimples like shape on the surface of surface film without rupturing the film. So as soon as the feet is lifted from the film, which is under tension, again becomes flat. So that you can see this a small kind of convex like shape here. This is actually due to the surface tension of the water. So due to which the surface tension acts as an inclined manner, the vertical component of the surface tension supports the weight of the spider. So as soon as the foot is lifted from the liquid film, which is under tension, again becomes flat. So this is another example for the surface tension. So the next example is suppose if you place a razor blade or a needle which you place gently into the surface of the water, which is actually floating on it, even though the density of the steel is actually nearly greater than the surface, nearly greater than the water. So the surface forms the surface film forms is due to the surface tension support the needle or a blade, and the thickness is not sufficient to break the film. Suppose if you keep this razor in opposite direction, the perpendicular direction, the force acting on the surface area is very small, so that it is actually rupture the layer, so that the density is actually the blade is actually the razor or a needle actually going out inside the liquid due to the density of the corresponding material. So another popular example for the surface tension is the paintbrush, which is actually immersed in the paint or in a liquid or in a water. So suppose if you keep the brush in air, you can see that the bristles are spread out like shown in this figure. Suppose if you keep this brush dip into the water, then you can see this So the brush is dipped into the water, and if you taken it out, the bristles are actually drawn close together due to the surface tension of the film, because this and the water between this bristles is actually trying to contract each other, so that the bristles actually sticking one another due to this due to the water between this the bristles. So all this simple example shows that the surface of the liquid behaves like an elastic membrane, which is under tension due to the which is actually having the tendency to contract. So this tension or pull of the surface of the liquid is called the surface tension. So apart from that, you can also have a many real other examples for the surface tension. For example, the rainwater does not pass through the tiny holes in the fabrics of the umbrella or tents or raincoats, because on account of the surface tension, the holes are blocked by the fine films of the water. Similarly, suppose if you consider a soap which is dissolved in water, then surface tension of the soap solution is greatly reduced, and this enables soap solution to quickly spread over the large areas. So this is one of the reasons why the soap is actually used for the washing. Similarly, the soap is used in toothpaste, and which is actually enable the paste is quickly spread out to the larger area, so that it is actually used as a quick mouthwash. So similarly, you have very many explanations and examples for the surface tension in a real world scenarios. So if you define the surface tension in a physics point of view, so it may be defined as the force per unit length. So the surface tension, which is equal to the force per unit length, or you can define it as the energy per unit area. So you can define either way, force per unit length or energy per unit area. Suppose if you consider this the force per unit length, then the unit SI unit of this surface tension is actually Newton per meter. Okay. So if you looking into the surface tension in a molecular level, and between any two molecules there exists a force of attraction. So this force of attraction is called the intermolecular forces. So this intermolecular forces actually have two types. So one is the cohesive forces. So another one is the adhesive forces. So if you consider this cohesive force or a cohesion, the attraction for which is the attractive force, both are actually attractive force, but if you consider the cohesive force, this cohesive force is the attraction between the two different molecules. So the two same molecules, the two molecules of the same substances are called as the cohesive force. That means the attraction force between the two molecules of the same substance. For example, if you consider the water, so the force of attraction between the two water molecules is actually for example for the cohesive forces. So on the other hand, this adhesive forces is a force between the different substances is called the adhesive forces. For example, the attraction between this water molecule and the glass molecule. Suppose if you consider the glass of the water which is actually poured in the glass, and if you remove the water from this glass, then the attractive force between these two molecules of the same substance is called, and this cohesive force is actually cohesive force between these two molecules, two water molecules, is actually very less compared to the adhesive forces between the glass and the water molecules. Therefore, there is a strong attraction between the water and the glass molecule, so that the water is actually stick with the glass. So in contraction, suppose if you take the mercury into the glass in a glass plate or a glass tumbler, so the cohesive force between its molecules is very strong compared to the adhesive forces between the glass and the mercury. Thus, there is a strong attraction between the mercury molecules and almost no attractive force between the glass and the mercury molecules. Therefore, the mercury does not actually stick with the glass or any other substances. Suppose if you take any mercury in any substances, the mercury is the cohesive forces between the two molecules of the mercury is actually very strong than the any other adhesive forces, so that the mercury will not actually stick with the any surface. So the forces of attraction between the any two different substances or two different molecules is actually known as the adhesive forces, and the force of attraction between the same molecules is actually known as the cohesive force. And suppose if you consider any molecule, so this molecule is actually having the some force of attraction between around this, which is having the some circular spherical shape. So the maximum distance to which the molecule is exerting the force of attraction to the another one is called as the range of the molecular attraction. So this range is actually known as the molecular attraction, which is actually generally in the order of 10⁻⁹ meters. So that if you consider a sphere of a molecule and the molecule is actually at the center of this range of the molecular attraction, then the radius is actually called as the sphere of influence. Of the molecule. So the molecule attracts and is in turn attracted by the molecules present inside this sphere. So if you draw a sphere around this molecule and taking the radius equal to the range of the molecular attraction, and the center as the center of the molecule, which is actually the sphere of the influence, so that the radius is actually equal in all the directions. So which is actually known as the sphere of influence. So one can explain the surface tension using just explain the surface tension using the molecular theory. So if you consider the three molecules A, B, C into the water molecule which is in the liquid, so such that this the molecule A is actually well inside the liquid, and the liquid molecule B is actually close to the surface, but most of this part of the molecule is actually inside the liquid. However, it is actually very near to the surface of the water, surface of the water. On the other hand, you can consider another molecule C, which is actually exactly on the surface of the water. So the larger circle is actually indicating this the sphere of influence of the any molecule. So the arrow marks which are actually indicating the molecular attraction. So if you consider this spherical the molecule A, so which is actually completely inside the liquid, and hence it will be acted upon the force of attraction is actually equal on all the directions, and thus the forces will balance one another, and the net force acting on the molecule A is exactly 0. For example, another molecule, the molecule B, the part of the upper half of the sphere is actually influenced by influences in the air, which contains air molecules. So the air molecules are exert very negligible adhesive force to this molecule B. Therefore, the cohesive forces due to the molecules in the liquid remains unbalanced, and thus the net force actually acting on this molecule is actually downwards, because all the molecular attraction is actually due to the water, so that the molecular B is actually experiencing downward direction force. And if you go for the molecule C, so the upper half of the sphere is actually influenced completely by the air, and due to this, the force of attraction due to the molecules inside the lower half of the sphere will remains unbalanced. Thus, the molecule experiences the maximum possible unbalanced force in the downward direction. Therefore, the resultant downward force in this case of molecule C is actually maximum, so that the molecules on the surface of the water and in a surface film of thickness equal to the range of the molecular attraction of the liquid of the molecule, which is experiencing a net force which is actually in the downward direction. Therefore, the magnitude of the force depend upon the distance of the molecule from the free surface. So this behavior of the film is actually different from the rest of the liquid inside the water, so inside the water level. Therefore, this thin film is actually behave like a film which is under tension, and this phenomenon is actually known as the surface tension. So if you try to explain the surface tension in the form of energy, suppose if any molecule is brought into the surface from the liquid, the work done is to be done against this net downward force. So this upward force is actually which is actually stored as a potential energy into the corresponding molecule, water molecule, and this work done is actually increases the potential energy of the surface, but the liquid surface will have the tendency to have the minimum potential energy. So the minimum number of molecules remains on the surface of the liquid, so that the surface of the film tends to contracts, and due to this reason, this surface the surface of the water is actually contain very minimum number of molecules. Thus, the surface of the liquid is under tension behaves like a stretched elastic membrane. Suppose if you want to define this surface tension in the form of energy, then the potential energy per unit area of the surface of the film is called the surface energy. So the surface energy is equal to the potential energy per unit area. Okay, so next we are going to see about what is the work done to increasing the area of the surface. So in order to do a small experiment, we are going to consider the rectangular framework of wire, which is having the sides of A, B, C, and D. And so we have another horizontal wire which is having that is EF, which is actually placed across it, which is actually allowed to move freely up and down in the rectangle wire. Suppose if you take this rectangle bar into the soap solution, and if you dip into the soap solution, then the foam of soap is actually formed in this area of B, C, F, and E. And this soap solution is actually having some certain surface tension. Therefore, the surface tension of the soap is actually trying to pull this wire, then the horizontal wire EF, upwards towards the BC, which is actually perpendicular to this EF, perpendicularly upwards towards perpendicular upwards to the EF. Therefore, in order to keep this EF, horizontal wire in the same place, there will be another force which is actually acting opposite towards the surface tension force. And if you consider that force is actually taken as a F, which is actually trying to make an equilibrium. That means it takes the horizontal wire to the same place, which has to be applied downwards. Suppose if you consider the sigma is the surface tension, that is the force per unit length, and L is the length of the wire. That means the length of the horizontal wire EF. Then the upward force due to this surface tension can be written as 2 times of L into sigma. That is the upward force. The 2 is because this film is actually having the two surfaces, and each has the two surfaces in the top side and the bottom side of the liquid. So which is actually have the two times of the surface tension, so that you have the 2 times of sigma, that is the surface tension. Therefore, if you consider the F is the surface tension, then the F is the force which is actually acting downwards, which is actually equal to this the same force, so 2 times of L into sigma, so that making the horizontal wire EF in the same position. Suppose if you try to apply another force to pull the horizontal wire to the another new position called the E prime and F prime, and is actually moved through a small distance of x. That means the difference between the EF and the E prime F prime is actually taken as a x. Then the work done to pull this wire from position EF to E prime F prime, that is can be written as, that means the work done in increasing the surface area of the liquid, which is equal to force into the distance. The force we already know that is 2 times of L into sigma into x. So that is the work done. is the work done, which is equal to this the surface tension and multiplied by the increase in the area of the surface. So that's the work done to increase the surface of the liquid by unit area can be given by the ratio of a sigma, 2L size of sigma into x divided by 2 times of L into x, which is equal to 2 times L, which is equal to sigma. So this is the work done in increasing the surface area of the liquid film by the unit surface. Okay. Therefore, the surface tension of a liquid may be defined as the amount of work done in increasing the surface area of the liquid by liquid film by a unit T. So this work done is actually required to enlarge the surface of the separation between the two immersible or a partially miscible liquid is called the interfacial surface energy, and it is often expressed as the interfacial tension in Newton per meter. Okay. So based on this work done in increasing the area of the surface, then I can solve a simple example problem. The problem is, so we have to calculate the work done in spraying a spherical drop of water of 1 millimeter radius into a million droplets. So all of the same size, the surface tension of the water is given as 72 into 10 power minus 3 Newton meter. So in this problem, we are actually trying to breaking the droplets into the millions of droplets. That means you are actually increasing the surface area. Therefore, how to do the work has to be done for this purpose. So this work done is equal to the surface tension multiplied by the increase in surface area. So in order to calculate the work done, we have to first find out what is the increase in the surface area. So first we have to calculate the increase in surface area. Suppose if you consider the R is the capital R is the radius of the large drop. Radius of the large drop of water, and if you consider the small r, which is actually the radius of the small droplet. Therefore, the total volume of the original drop, which is actually separated, split into millions of droplets, so that the volume of 10 to the power 6 droplets. So this volume of the original drop is actually equal to the volume of the 10 power 6 water droplets, so that you can easily find out the volume of the sphere, which is actually nothing but the 4 by 3 times of 5 times of r cube, that is a large droplet, which is actually equal to the 10 to the power of 6 times of 4 by 3 times of pi into the small r cube. So this is actually the volume of the original drop, and this is the volume of the 10 million drops. So the radius of the large water drop is given as 1 millimeter, so that I can substitute the value here. So that 4 by 3 pi times of 10 to the power minus 3 times of cube, which is equal to 10 power 6 into 4 by 3 pi into r cube. So from this relation, I can easily calculate what is the r value. Just this 4 by 3 pi and 4 by 3 pi will get cancelled, so that the r cube, which is equal to 10 to the power minus 15 times of meter, because this is 10 power minus 6 and this is 10 power minus 9 and this is 10 power 6. So if you take this 10 power 6 this side, you can get the 10 power minus 15 meters, or this r, which is equal to 10 power minus 5 times of meter. So this is the radius of the small droplet. So next we can easily find out the area of the original droplet. Which is equal to 4 pi r squared. So the value of r is again 1 millimeter, so that I can substitute the value 4 into pi into 10 to the power minus 6 times of meter squared. Similarly, I can also calculate the area of the small droplet, which is equal to again 10 to the power of 6 times of 4 pi small r squared, which is equal to 4 pi times of 10 to the power minus 4 times of meter squared. Therefore, the increase in surface area is this is equal to this 4 pi into 10 to the power minus 4 minus 4 pi into 10 to the power minus 6 meter squared, so which will be equal to this 1.244 into 10 power minus 3 meter squared. So this is the increase in the surface area. So this is the increase in surface area. So once if you know the increase in surface area, you can directly substitute it with the same formula, that is the work done. So the work done, which is equal to the surface tension. So the work done, which is equal to the surface tension into multiplied by the increase in surface area. Which is equal to the surface tension of the water is given in the problem itself, which is 72 into 10 power minus 3 Newton meter. So 72 into 10 power minus 3 into the 1.244 into 10 power minus 3, which finally which is equal to 8.956 into 10 power minus 5 joules. That is the total work done in spraying a spherical drop of water of which is having the radius of 1 millimeter into the millions of droplets. This much work you have to do this for this purpose. So similarly, you can also calculate the work done to blow a bubble, blowing a bubble. Suppose if you consider the bubble is actually having the radius of r, so the bubble is having the radius of r, and this bubble is actually having two different surfaces. One is the inner surface. Suppose if you consider this is the bubble, and you have a inner surface as well as the outer surface. So each of the surfaces are equal to this 4 pi into r squared. Therefore, the surface area is, so the surface area of the film forming the bubble is actually 2 times of this 4 pi r squared, 2 times of 4 pi r squared, which is equal to 8 into pi into r squared. And then work done to blowing the bubble is, the work done to the blowing a bubble is actually the surface tension multiplied by the surface area of the film formed, which is actually equal to surface tension. If suppose if they take the surface tension as taken as sigma into the surface area is taken as 8 pi r squared, so that 8 pi r squared into sigma is the work done to blow a bubble. So if you know the radius and the surface tension of the bubble liquid, then you can easily find out what is the work done is. And suppose if you consider a soap bubble which is actually slowly enlarged from the radius of 0.1 meter to a radius of 0.2 meters, you have to calculate what is the work done to blow the bubble from a radius of 0.1 to 0.2 meters. So consider the surface area of the soap liquid is actually 30 into 10 power minus 3 Newton per meter. Then we have to first find out what is the increase in the surface area. So the increase in the surface area, which is actually equal to the 8 pi times of the difference between the radius, that means r2 squared minus r1 squared. So r2 squared is taken as 0.2 the whole squared minus 0.1 the whole squared. So the final answer is 0.7536 into meter squared. So this is the increase in the surface area. So once if you know this increase in the surface area, you can directly calculate the work done. So the work done is, this is equal to surface tension into the increase in surface area. Sorry. So the surface area of the bubble is, the soap bubble is actually given as 30 into 10 power minus 3 Newton meter into 0.7536 meter square, and the final answer is equal to 0.02261 joules. So this is the work done to blow the soap bubble with the enlarged radius of 0.1 to 0.2 meters. Similarly, I can solve one more problem related to this. The problem is, so what is the work done in blowing a soap bubble of radius 0.1 meter? What is the additional work will be performed in further blowing it so that its radius becomes 0.15 meters. So you have given the for the starting radius is 0.1 meter and the final radius is 0.15 meters. You have to find out what is the work done. The additional work done will be performed for blowing it. So the surface tension of the soap liquid in the soap liquid is actually given as 30 into 10 to the minus 3 Newton per meter. So in order to solve this problem, first we have to find out what is the work done blowing a soap bubble for this 0.1 meter. So the work done in blowing a soap bubble of radius 0.1 meter. So you know this formula, that is 8 pi r square into sigma. Let us take this as radius as r1. So that's 8 pi r1 squared into sigma. So 8 pi into 0.1 squared into 30 into 10 power minus 3 Newton meter. The final answer is 7.536 into 10 power minus 3 joules. So this is the work done to blow the soap bubble with a radius of 0.1 meters. And then now we can calculate the work done in blowing the radius of the soap bubble from 0.1 to 0.15 meters. So work done in blowing the radius of soap bubble from 0.1 meter to 0.15 meters. So which again you can use the same formula, 8 pi into r2 squared minus r1 squared into sigma. So here this r2 is actually 0.15 and r1 is 0.1. So 8 into pi into 0.15 the whole squared minus 0.1 the whole square into 30 into 10 power minus 3 Newton meter. The final answer is 9.42 into 10 power minus 3 joules. So this is the work done blowing the radius of the soap bubble from 0.1 to 0.15 meters. Okay, so I hope you understand what is the surface tension and how to calculate the work done to increase the surface area of the surface area of the any liquid. So I stop here, and the remaining sessions I will take it in the next video. Okay, thank you.